I work in theoretical physics division, Petersburg Nuclear Physics Institute in St. Petersburg in Russia, a senior researcher. For the last 20 years, I'm privileged to collaborate with Viktor Gorshkov, who actually is my teacher, and all I know and I could achieve is due to his inputs into me as a student first. And as theorists, it is a great pleasure and honor for us to be invited here, because actually theorists, what they are doing, they are trying to make a coherent picture of the world, such that all fundamental laws of nature and all data fit together in a non-contradictory manner. It is, believe me, a hard work, and there is no more joy for theorists when people could make use of their findings. Not all theorists can boast such joy, because theoretical physics of today deals with very complicated matters which don't currently have a direct impact of human life. And so for us it is very, very important to see this interest, and it encourages us to work more, and we will be happy to contribute all our knowledge to actually make some positive change in the world. So thank you very much for your interest, and we are completely at your disposal. So some history, how it emerged. Victor has, by training, he is a physicist theoretician, and for the first part of his career he worked in traditional theoretical physics very successfully. Russia had a very strong school of theoretical physics, but he also had a very strong interest in how nature works. It just appealed to him from his early childhood. And so in late 70s, 1970s, he changed his research agenda and began to find out how to use the powerful apparatus of theoretical physics to explain life. Because what strikes us when we look at living systems is that they are resilient, they are stable. Our civilization continuously faces some problems. We run out of fuel, we run out of water, we have wars, and civilizations come and disappear, while life has persisted on land for nearly 4 billion years, and this process has never interrupted. So Victor formulated the biotic regulation of the environment concept, of which biotic pump is a very important part. So as scientists, we consider this the description of the biotic pump a very big luck. So my task now is to explain to you what is it and why it is new and perceived as new. Antonio mentioned that the change we are now witnessing is catastrophically rapid. So models that we have don't describe what is going on. But if we look at what happened in the past, can we describe past changes? And here it is well known in the literature that there are these puzzles or problems or questions of past climate. And one of such puzzles are the abrupt changes of monsoon circulation. Do you know monsoons that bring water seasonally? Yes, and on which many actually more than billion people currently depend. And so the matter is that current models cannot explain these changes. Here you can see actual data on oxygen isotopes, which show the two such abrupt monsoon events, which happened 16,000 years ago, this is the left panel, and 4,000 years ago. And both led to disappear. 4,000 years ago, it was followed by the urbanization of India. So it was a decline in cultural level, and also the earlier transition also impacted earlier human populations very drastically. And so there is the problem of modern climate, for example, the wet season in the Amazon. Current understanding, I will be talking about it, of the climate is that it is driven by temperature contrasts. Why do monsoon happen? Because sun heats the earth in summer, so the earth gets warmer, warm air rises, and so there is rising air here, and from the cold ocean there is airflow to land. But when scientists look at the Amazon, they find at the southern Amazon, it is not shown here, but they find that this wet season onset occurs several months earlier than the sun actually comes. Here you can see how the Earth's atmospheric circulation is organized. You see, there are these cells, two Hadley cells, and the air is rising where there is blue arrows, and you see near the equator the air is rising, right? And because it is rising, it is raining. Pressure is low, you can see this, and there is much rain. And so the seasonal migration of this convection zone, people think, is what accounts for the wet season in the Amazon. But in fact, it appears that it starts earlier, and scientists don't know why, and there are debates why it is so. And now think, if we cannot understand such things, both are connected to water, you see. So perhaps what is happening so rapidly now is also connected to water, not to CO2, because neither CO2 nor temperature underwent such drastic changes when this monsoon circulation collapsed. This is what puzzles. If they knew that there was a drastic change of temperature, they say, oh, okay, that is what we know. Temperature changes, monsoon changes. But seemingly nothing changed. But the monsoons collapsed. You see, so this is just a small preamble, what the situation when we came with the biotic pump. You see, this is the water cycle on land. Moist air comes from the ocean, right? For it to be rain, the air must rise. You know, some people think that when it rains, the air goes down. This is not so. This is not so. It rains because the air goes up. Because as it goes up, it cools, right? So moisture condenses and goes down. But since our land is elevated over the ocean, the water goes away, like you see runoff. So if there is no this continuous import of moisture from the ocean, the process stalls and the land becomes a desert. And what we proposed, how biotic pump was formulated, is that this process is, the key for this process is forest transpiration, because forest adds water vapor to the atmosphere, and so when the air rises, condensation happens, and the whole process goes on normally. So you see, the air, you see this, so there is evaporation from the forest. You see these arrows. The air gives moisture away, right, in order to receive more than that. So this is like an investment. For economists, it should be understandable. You invest your money to get more in return. But if you invest in a silly manner, you just lose your money. And this capitalizes the problem. If we grow the wrong trees, they will evaporate when no condensation can be switched on, and we will just lose all our water resources. So it is very important that we learn from nature how to make this investment into the atmosphere in the right manner. And I will tell you our answer from the very beginning. It is such a complex system that the only thing we can do is to restore natural forests. So give the forest 50% of your area and it will work for you. The areas nearby will get moisture from it. It will be like an ocean. So we cannot hope, this is our firm position, we cannot hope to replicate it and to study all the details. Now I can tell you, I want you to have some idea why it was new. And how it relates, it is important, how it relates to the conventional picture. A small aside comment. In our theoretical physics division, there are really very strong people working. Not me, I'm just trying to learn from them. But they are really good professionals and theoreticians. And I realized with years that a physicist theoretician can come to any field and make some original research, because he has a training of putting all things together, how they fit. So how they fit together. While specialists, as Antonio mentions, they are concentrated on their particular things and don't see the picture. And I even give you the number. When you come to the field and really are interested and want to make an impact, 7 or 10 years from your arrival to top-level publications in Nature and Science. In my career, we made, or other top journals, we made it twice. We first, with Victor, we came to Ecology, Metabolism, Life Metabolism. First publication in 2003. In 2009, we were already in Proceedings of the National Academy of Sciences and Science and Nature. And then in 2007, with the Biotic pump, these years, with our colleagues, last years, we made publications in top 5 climate journals. So, but it is not fast. So in a way it is fast, but it is 10 years of your life of intense work, very intense work, because you need to dig very deeply. You need to find errors, inconsistencies, and when you are finding other people's inconsistencies, they are not happy, so they are pushing you back. So you need to be strong emotionally, you must be convinced. But in any case, this is 10 years and you have already some reputation with which you can go further. And I want you to just have this idea, what is actually new that we have proposed. So it is we all know that winds are driven by pressure gradients. What is pressure? Air pressure. Air consists of molecules, right, which all collide, and pressure depends on two things: the number of molecules and how intensely they collide. That is on their temperature. So I cannot show it because it's on my computer, but you can. What is a pressure gradient? When pressure in one place is higher than in another. And you can achieve that by two ways. Either change the number of molecules or change temperature. And this graph, the lower one, shows you the pressure difference depending on height between two atmospheric columns. One is hot and one is cold. The difference is 10 degrees 10 degrees Celsius. You can see that because the warmer column is warmer, the pressure is bigger everywhere except on the surface, right? Because on the surface there is Earth's gravity, so on the surface the pressure is equal to the weight of the atmosphere, right? It is hydrostatic equilibrium, so it doesn't change. So suppose we took two columns and warmed one, so we have this pressure difference. And this is the essence of modern climate science. Now imagine that this big thing, big pressure in the upper atmosphere, pressure starts to leave from the column, right? It is like we pull this curve to the left, you see? And since some air has moved away, like in the graph above, pressure on the surface drops. So pressure is higher in the atmosphere and low at the surface. And on the surface there comes air. This is how monsoons, for example, are explained. You see? So first we warm, there is surplus of pressure in the upper atmosphere, it goes away and it comes back in the lower atmosphere. So as a scheme, it is perfectly appealing, right? Very, very logical. But the devil is in the details. The problem is that you have this qualitative idea of how pressure is modified, but you don't know how fast the air will be moving. And it is a very big problem because to calculate that you also need to know friction, how the atmosphere opposes the motion. And in the atmosphere, friction is of turbulent nature. You know these things. And turbulence is a very difficult theoretical problem and nobody knows how to solve it. So actually current models just fit the winds, fit the turbulence in such a manner that the circulation fits the observations. This is how all our global circulation models, which are behind the IPCC, which are all presidents of all countries accept as current science. In fact, this is the key element which is just fitted. It is not that it is not discussed. It is. But there are very few high-level climatologists who know that, and they are discussing, but since there is nothing doing, what you can do? You can adjust. So this is the main Achilles heel. And why our work received such tracking? It is not just because we came and said, oh, guys, remember there is another factor, the number of molecules. You just use the temperature. If we account for the number of molecules, you are okay. No, we calculated from theory, developed a theoretical concept which allowed to predict how much wind will be generated based on our effect. So it was just a formula relating wind power to condensation rate. And then we used observed data both for the global circulation and for hurricanes and tornadoes, which are intense condensation events, to test our theory, which we people ask, do you have any verification? We do, because when in 2007 we published the biotic pump concept, we still didn't have those calculations and had no idea what is the number for the power of global circulation. Just no idea. We were newcomers. And then when we did those calculations and testing empirical data, it was for us a very revealing thing that everything fit. And so people had to face this our theory, because it makes verifiable predictions. And so this is what is due, and this is what also explains the radical shifts in monsoon systems, which cannot be explained on the basis of temperature. So, once again, how it works: forest moistens the air, moisture rises and cools, there is pressure drop, where condensation occurs, it pulls the air upward, there is pressure shortage at the surface, and then dry air returns to the ocean in the upper atmosphere. And so the key process is the air moistening by the forest, because if the atmosphere is dry, there is no condensation-driven winds. And so there is the data for, we also analyzed precipitation distribution across major forested and non-forested basins. But this is what I show you. You see, this is moisture pump in Eurasia. This is what works for the entire continent. How it works, you see? In winter, when the forest is dormant, this is what is shown here is precipitation, right? And this is distance from the Atlantic coast at the 60th degree northern latitude. So this is all, in just a moment, I will show you the map again. You see this white arrow, long white arrow, 7,000 kilometers, this Eurasian Boreal Forest Belt, which works for all of us. And so what we found, you see, this is precipitation. When forest is dormant, all rain is concentrated over the ocean. And only when trees are functioning, you can see that rainfall goes away. Look, here it is over the ocean. Now spring comes and rain is distributed over 7,000 kilometers, almost in a uniform manner. So the biotic pump works, and on the ocean it declines. When the forest sleeps, the rain returns to the ocean. And you see this peak at the border of the... What happens if we destroy the biotic pump? The forest will not draw moisture inland, but since it evaporates from the ocean anyway, it will rain in the coastal areas, and there will be catastrophic floods. So I'm finished. This is a picture. Oh, I'm sorry. So, but I think it is already. If it is time, I can finish just because I.
It's okay.
It disappeared somehow.
We have enough time for everything. That's why we came together. So.
I don't know what happened.
What this one? So this is a picture of a Yenisei tributary, which was later flooded. So this place doesn't exist, but it shows the Siberian part of the Biotic pump. And here I will show you, this is a more global picture. These are the Amazon forest, Congo forest, so Atlantic transect, right? And the same boreal forest which we saw, and Australia. You see the lower right panel. And this red line is the ratio of precipitation on land to the mean oceanic precipitation at this latitude. And we can see, what we can see, the Amazon forest and Congo forest, basically, on average, the black line is the mean, the annual mean. For the most part of the year, they win the tug of war with the ocean, so they draw moisture inland. The boreal forest does so only in summer because it is seasonal forest, right? And Australia is locked for moisture year-round. So we know that there is wet season and there is dry season, but in neither of them moisture penetrates inland. You see, it rises, but yes, it is, and very little. So we can see that there is no this pumping. And if we look at temperature, this is temperature actually comparing Eurasian Boreal Forest and Australian desert. Take a look at the, this.
Hard to see because the cursor is very small.
Sorry. Actually, the basic point is the third graph to the third graph from the left. It is the surface temperature difference between between the land and the ocean, and we can see that the boreal forest is 5 degrees warmer in summer, of course, but Australia is same 5 degrees warmer during the rainy season, which is in January in Australia. And so, but despite this temperature difference, it still cannot draw moisture. And winds, this is the fourth graph, are stronger in Australia. And there are winds on sea, but they don't penetrate inland. Meanwhile, in boreal forests, winds are less intense, but they bring moisture, and there is this moisture transport. And so what we have deforestation consequences for the water cycle. And what I would like to send this message, because we do need to restore green life, which is the smart biotic pump is about. But we also need to protect what we still have. And because if we shift the emphasis on restoration, people can think that, oh, we will restore everything. Let's cut it, because in Russia there are strong deforestation. So we need to somehow to make this connection all the time. And there will be, if we destroy the biotic pump, there will be severe floods and drought. So floods and droughts go hand in hand, because there is meta-conservation. You see, what the forest draws moisture regularly over big territories. Everybody's happy. When it is destroyed, all moisture randomly, the process becomes absolutely random. It can fall down anywhere, and all the others will be without water. one more thing that I want to tell you. It is an ecological dimension, that forest must be competent to run the biotic pump. You see, there is this forest succession process for forest recovery. We first have shrubs, grasses, after some disturbance like fire, which only with time they are replaced by trees. So, if we are lucky, our grandchildren will be walking in such forests. So, this dimension should also be stressed, that we are working for the future. We are not just securing for ourselves some 24 years of better comfort. We send message through centuries, such that people will remember us, and walking under this forest along the brooks and rivers, they will remember us with gratitude for our consciousness and dedication. But we must have this picture in mind, that forests, and at this early stage, when you have grasses, it cannot regulate the water cycle. Why? Because you need to evaporate when it is needed. For example, the atmosphere is a turbulent system, that there are many winds going there and back, and so if the situation is very unfavorable, it is better not to emit moisture. And so, for example, recently, yesterday, Douglas Scheel, who will come tomorrow, shared with us an article about forests and water, who explained why this topic was not popular among climatologists. Because in late 19th century, there was an idea that people should go to the desert in the US and grow cereals there, and the deserts will be green and moist. And people went, grew cereals, and nothing happened except for the big dust bowl. And so this idea was discredited. But it was discredited, if you asked me, I would say it will happen with 100% certainty, because grasses cannot control transpiration. To control transpiration, you need closed canopy, because under this canopy, there is a temperature inversion. So the canopy under the sun is warmer than the soil. And because of this temperature inversion, there is no uncontrolled rise of moist air, and so all evaporation is under control of the leaves. So it is a controlled, highly ordered process. When you have grasses, they are just at the mercy of external conditions. And for example, but it is not just the distinction between grasses and trees. There are more refined distinctions, because, for example, when you have evergreens, you see, it is for the European climate, it does matter when we have this seasonality. And you have the evergreens and the deciduous forest. When spring comes, the evergreens already have their leaves, right? And then they can already work. The biotic pump can work. And so they can ensure a smooth seasonal transition, drawing moisture from the Atlantic Ocean, spreading it. While when you have cut the forest and it is replaced by early successional trees like birch, spring came, there is sun, but the biotic pump doesn't work because there are no leaves, right? And so it is only when the leaves appear, the trees suddenly begin to draw moisture, and there are sharp fluctuations which we are witnessing recently in Europe. There are very cold springs and cold summers, and then so it became a chaos. So it is very important that the right trees are So the forest is hydrologically competent. And this is my last slide for now. And why there is this conflict? Because of commercial value of forest and their hydrological competence. Because commercial value is when the forest grows most rapidly. After 50-70 years, it is not already such so much biomass increment, and so they decide it is time to cut, right? But actually, the most important trees are the older trees. It is like a well-educated, trained man and a boy. You see, and they, so to speak, they send to the war boys. And they are killed. So they don't allow the forest to develop to its mature stage when it can work for us. So deforestation that currently occurs in Russia, it is a pan-European business. It is our common problem, because in Russia, you see, there are no environmental discussions. Nobody cares. Nobody cares about CO2. But there are people who love forest, including our president. So if this topic is properly advertised, it could make a resonance, and without solving this problem in Russia, we won't guarantee a stable climate in Central Europe. So it should be one of the strategic. So I'm finishing now. Thank you very much. I have lots of, can talk for hours about